Okay, so we're going to give a short video on balancing equations, and that's going to help. We'll do more of this when we get to our weekly session, but I just want to introduce the topic of balancing equations. And before we do any of that, let's go over some basics, and then we'll dive into the balancing of equations. So what are we going to learn from this video? Well, we're going to learn what a chemical reaction is, how what do we use chemical reactions to describe, and then from there we're going to talk about balancing, why balance equations, and then the balanced equation gives us another piece of information, which is it gives us the stoichiometric coefficients, which we're going to talk about later on in this video. And then we want to ask the question, what can we do with stoichiometric coefficients, which leads to the question of stoichiometry and how you use stoichiometry to tell you the relationships between the different compounds that are reacting. Let's jump in. What's a chemical reaction? A chemical reaction is exactly that. It's a reaction between elements or atoms or molecules, but a more concise way to say that is it's a process that involves the rearrangement of the molecular or ionic structure of a substance, right? So you take two compounds, you react them together, and something happens such that you go from reactants to products. We're going to talk about that more in a second. So these are the different types of reactions, right? You have combination reactions, you have decomposition reactions, single displacement, double displacement reactions, combustion reactions, and also redox reaction. Anyway, let's go on to the next slide, which kind of depicts some of these reaction types. So you can see a combination reaction. You have sodium and you have chlorine. You have two elements. You combine them together to make a compound, right? And a decomposition reaction, that's basically the reverse of a combination, right? So you have water, and then you break water up into its constituent components, which are hydrogen and then oxygen. Single displacement is just that you have a single element or an atom, and that's going to displace an atom in another compound. So in this particular example, you can see that zinc is replacing copper in the product shown here, right? And then a double displacement, you see you have uh, KCl and then sodium nitrate, right? This is the same as single displacement except for you have what's called a metathesis where both partners are going to switch. So the K and the silver are going to swap places, and then the chlorine and the nitrate are going to swap places. And you can see that in this particular product shown here. And you have combustion reactions where a compound is reacting with oxygen gas. And basically that's a reaction where you burn something up, right? And then the redox reaction is a little bit different. It's the exchange of electrons. So the redox is short for reduction, oxidation. So reduction is the gaining of electrons, oxidation is the loss of electrons. And so a redox reaction happens between two atoms or two compounds where one of those is going to give up electrons or lose electrons, and one of those is going to gain electrons. All right. So let's talk about chemical equations. Right. I have here on the screen words: potassium chloride plus silver nitrate yields silver chloride plus potassium nitrate. That means absolutely nothing. Right. We can't balance that. We can't figure out the stoichiometry. We can't figure out the coefficients. We can't figure out anything. So we have to have a way to illustrate a chemical reaction, right? We can say what's happening, but we need a way to illustrate that. So the way we illustrate it is by showing that those words in the form of a chemical equation, where we take the elements from the periodic table and combine them to make our compounds, and then we write those compounds out here, right? So you can see potassium chloride is K for potassium and Cl for chlorine, so potassium chloride. And then silver nitrate, you have Ag, which is silver on the periodic table. And then the NO3, that's the nitrate anion, and it's what we call a polyatomic, which we'll talk about later, right? And you might want to go ahead and Google polyatomic ions so you can see the list and start memorizing that. And then on the other side, you have silver chloride and then potassium nitrate. This is an example of what we call a double displacement, where silver and potassium swap places, and then the chlorine and the nitrate anion swap places. All right. So chemical equations graphically illustrate chemical reactions, right? That's the purpose of writing down a chemical equation, to graphically illustrate a reaction that you want to discuss. All right. So now let's talk about balancing. In this particular slide, I have copper sulfate and iron solid, and that's reacting to give me uh, iron 3 sulfate plus copper solid, right? What you'll notice is that there's a slight problem here, and this is the crux of balancing equations, right? There's not the same number of atoms on each side, and that's not possible, right? And we're going to talk about why later, but in a chemical reaction, you can't end up with less or more than you started with, right? So you have to have the what you put in, you have to get out, right? So we're going to talk about that. But the way we handle this is by what we call balancing this equation. Balancing means that I'm going to ensure that there's the same number of atoms on each side of the reaction, all right? So let's start with iron, right? Notice on the right side and the product side, there are two iron atoms here. And so on the left side, I need to make sure that there are two iron atoms. And so what I do is I put a coefficient in front of iron, right? A 2. That 2 means that now I have two irons on the left side of the reaction. If we look at the sulfate, SO4, which is in parentheses, there are three of those. And so if I want to balance that, I can put a 3 on the left side in front of copper sulfate. But now that means I have three coppers and three sulfate anions, right? Three SO4 polyatomic anions, right? And so now I need to fix that on the right side because now I have three coppers on the left and I have one copper on the right. And let me just back up a second. All of your coefficients are understood to be 1 unless you put another number there. So in front of the copper, that's understood to be 1. But I need to increase that to make the number of coppers on the right match the number of coppers on the left. So I put a 3 in. And so now this equation is what we call a balanced equation, where there are the same number of atoms on the left as there are on the right. And the question I know you're asking, why do we have to do this? Well, this is science. And in science is based on rules and principles. And so there is a rule of thermodynamics that says this, that matter can neither be created nor destroyed. Matter can only be rearranged. And so again, I can't have less or more on the product side than I have on the reactant side, and then vice versa. So I have to balance that equation to illustrate the fact that what I start with, I also end with, and as far as the number of atoms are concerned, right? So that's why we balance equations. So now that's why this equation is now correct because I have the same number of atoms on the left that I have on the right. All right, so what can we do with these numbers? These numbers that are in front of these compounds or elements are called what we call stoichiometric coefficients, right? And stoichiometric coefficients give us the relationship between the compounds and the reaction, right? The stoichiometric coefficients tell us the ratios of the different compounds, right? So if I look at copper sulfate to iron, I can say that those two exist in a 3-to-2 ratio, right? If I look at copper sulfate to copper solid on the other side, I can say that those exist in a 3-to-3 ratio or a 1-to-1 ratio, right? Copper sulfate to iron sulfate. Copper sulfate exists in a 3-to-1 ratio with iron sulfate. What does all of that mean? It means that I'm able to convert from one compound to another using that ratio.
Let's say if I had 100 moles of copper sulfate, right? And I wanted to figure out how much iron sulfate that would give me. I could figure that out using the stoichiometric ratio because we know here the ratio is 3 moles of copper sulfate is equal to 1 mole of iron sulfate, right? So in order to determine how much iron sulfate I get from copper sulfate, I just use the stoichiometric ratio. So I have 100 moles of copper sulfate, and I'm going to multiply that by using the stoichiometric ratio. I want to find iron sulfate. I want to find iron sulfate. So I put that in the top, 1 mole of iron sulfate, and in the bottom I put 3 moles of copper sulfate. So I can convert from copper sulfate into iron sulfate using the stoichiometric ratio, right? And so basically that's going to give me, and I'm just going to go ahead and multiply this or divide this out, 33.3, right, moles of iron sulfate, right? And I can do that with any of these terms, right? I can convert between copper sulfate and iron, copper sulfate and elemental copper, iron and iron sulfate. It doesn't matter. I can convert between any of these quantities using the stoichiometric ratio, right? I can convert any of them.
So now let's look at some examples. Let's look at the top example. You have sodium sulfate, iron solid, giving you iron sulfate, and then sodium solid. And the question is that balanced? And the answer is no. So in order to balance it, I need to put two sodiums. I need to have two sodiums on both sides, right? So if I put a 2 in front of sodium, that rectifies that problem. Everything else is balanced. I have one iron on each side, and I have one sulfate ion on each side. Let's look at the second example, right? I have potassium phosphate, and I'm reacting that with iron 3 bromide, and then that's going to give me uh, iron phosphate and then potassium bromide. So I need to balance that, right? If you notice, I have 3 potassiums on this side. I only have 1 on this side. So I need to fix that by balancing the equation, right? I put a 3 in front of potassium, and that now gives me 3 potassiums, but I also have 3 bromides, right? So now look on the other side, and I have a Br3. That subscripted 3 means that there are 3 bromines there, right? So now that particular reaction is balanced. There's 1 iron on each side, there's 1 phosphate anion on each side, and then there's 3 potassiums on each side and 3 bromines on each side. All right, so now let's look at that last example, and I'm gonna balance that because it's not balanced, right? Um, if you look at the reaction, right, there are 2 potassiums on the left side, there are 3 bromines on the left side, and then there are also 3 carbonate anions on the right side and 2 irons on the right side. So now I need to fix that. So if I put a 2 in front of iron 3 bromide, notice I now have 2 irons and then 6 bromines. So now let's deal with bromine. So if I go over to here and I put a 6 here in front of KBr, now I have 6 bromines, but I also have 6 potassiums. Now I need to balance out the potassium. So if I put a 3 in front of potassium carbonate, that's going to give me 6 potassiums, just like on the other side, but it also gives me 3 carbonates. And that also takes care of that because there are 3 carbonates on the right side, right? So balancing equations takes a lot of practice, it takes a lot of reps, and the way you get better is to continue to do it until you master it. So, with that being said, what did we learn today? We learned about what a chemical reaction is. We learned about what a chemical equation describes, how to balance equations, why to balance equations, how to identify stoichiometric coefficients, and then also how to use stoichiometric coefficients. So, if you have any questions, you can reach out to myself or Ms. Harden, and we'll be happy to answer. Peace.